In this video, we're going to talk about thermal expansion. What happens to objects when they're heated or cooled? Well, let's find out. Let's say if we have a bar that has a length of L, and what's going to happen if we raise the temperature? Whenever you increase the temperature, a solid will expand. It's going to get bigger, and if you cool it, it's going to contract. It will get smaller. So if we raise the temperature, this bar will increase by an amount called delta L, which represents the change in length. So as you increase the temperature, delta L increases. If you decrease the temperature, delta L will be negative. It will contract. So the bar will be smaller if you cool it. Now, delta L is not only proportional to the temperature, but it's also proportional to the length. If you increase the length of the rod, the change in length will also increase if you, of course, increase the temperature. The equation that relates these two is this equation. The change in length is equal to alpha, which is the coefficient of linear expansion, times the original length, times the change in temperature. Alpha is a coefficient or a constant that depends on the type of material. So the change in length depends on the material, how long the bar is, the length of the bar, and also how much the temperature changes by. So let's work on some practice problems. An aluminum bar is 1.25 meters long at 20 degrees Celsius. The coefficient of linear expansion is 25 times 10 to the minus 6. And that's supposed to be Celsius to the minus 1. If the temperature is increased to 75 degrees Celsius, how much will the length of the bar change? So we're looking for delta L. So delta L is equal to alpha times L0 times delta T. The coefficient of linear expansion is 25 times 10 to the minus 6, and the units are Celsius to the minus 1, which is basically 1 over Celsius. The original length is 1.25 meters, and the change in temperature, final minus initial, 75 minus 20, the change in temperature is positive 55 degrees Celsius because it increased by 55, going from 20 to 75. So notice that the units Celsius cancel. So whatever unit L0 is in, that will be the unit for delta L. So L0 could be in meters, centimeters, it doesn't matter. These two will have the same unit. So in this problem, since L0 is in meters, delta L will be in meters. So now let's go ahead and calculate the answer. So 25 times 10 to the minus 6 times 1.25 times 55 is equal to about 0.00172 meters. So the length doesn't change much. So this is the answer to part A. That's how much the length of the bar changes. Less than a centimeter. So now what is the new length of the bar at this temperature? To find the new length, we need to add the original length plus the change in length. So it's going to be L0 plus delta L. So that's 1.25 meters plus 0.00172 meters. So this is about 1.2517, but you can round that to 1.252 if you want. So this is the new length of the bar. As you can see, it increased slightly. Let's work on this one. A solid plate of lead is 8 centimeters by 12 centimeters at 15 degrees Celsius. And we have the coefficient of linear expansion. It's 29 times 10 to the minus 6, 1 over Celsius. Now, what is the change in area and also the new area of the lead plate if the temperature increases to 95 degrees Celsius? So let's draw a picture. So the lead plate is 8 by 12. So this side is 8 centimeters and this side is 12 centimeters. If we multiply 12 times 8, that's a current area of 96 square centimeters. Now, it's important to understand that once we raise the temperature, we know it's going to expand, but it's going to expand in all directions. So, let me draw a new picture. If this side is L0, then it's going to expand by delta L. And if this side is W0 for the width, then it's going to expand this way by delta W. So not only will it expand to the right, but it will also expand down as well. So the length and the width will increase. So let's calculate the change in length first, and then we'll calculate the change in width. So delta L is equal to alpha times L0 times delta T. So alpha is 29 times 10 to the minus 6. The original length is 12 centimeters. And the change in temperature, final minus initial, 95 minus 15 is 80. So the temperature increases by 80. So the change in length is going to be .02784 centimeters. So what is the new length? The new length is going to be L0 plus the change in length, so that's going to be 12.02784. Now let's do the same thing for the width. Let's calculate the change in width. So that's going to be alpha, which is 29 times 10 to the minus 6, times, instead of L0, it's going to be W0, which is 8, and the change in temperature is still positive 80. So this is equal to 0.01856 centimeters. So now what is the new width? So W, which is W initial plus the change, is now 8.01856. So now we can calculate the new area, which is simply the new length times the new width. So let's make some space first. So it's going to be the new length, which is 12.02784 times the new width, which is 8.01856. It's not going to change much, but it does increase a little. So the new area is now 96.446, if we round it, square meters. So therefore the change in area is the difference between these two values. So delta A is about 0.446 square meters. If you want to come up with a formula that can help you to get this answer, here's what you need to do. The formula is delta A is equal to L0 W0 times 2 alpha delta T plus alpha squared delta T squared. Now, because alpha is so small, it's 29 times 10 to the minus 6, alpha squared is going to be very small. So the contribution of this term is negligible. So we could say that delta A is approximately equal to L0 W0 times 2 alpha delta T. Now L0 is 12, W0 is 8, alpha is 29 times 10 to the minus 6, and since I'm running out of space, let's move this somewhere else. And the change in temperature is 80. So 2 times 12 times 8 times 29 times 10 to the minus 6 times 80 is about 0.4454. As you can see, this answer is very close to this one. Now keep in mind, I rounded this answer. So they're very close. So that's how you can approximate delta A. But if you want to derive the equation, here's what you need to do. So we know that delta L is equal to alpha L0 delta T. And the new L value is L0 plus delta L, where delta L is alpha L0 delta T. So we can factor out L0. If we do, it's going to be 1 plus alpha delta T. So that's L. If that's L, we could say that W is WO times 1 plus alpha delta T. Now, the original area is the original length times the original width. The new area is the new L times the new width. So therefore, the change in area is the difference between the new area and the original area, which is LW minus LOWO. So delta A is equal to the new L times the new W. Now the new L is basically this value. It's L0, 1 plus alpha delta T. So we replace L with that new value. Now we're going to replace W with what it's equal to here. So W is WO times 1 plus alpha delta T, and then minus L0 W0. So notice that we can take out an L0 and we can factor out a W0. So let's go ahead and do that. So this is going to be L0 W0, and notice that we have these two terms, which, since we have two of them, we can write them as 1 plus alpha delta T squared, since we have two of them. And we took out both L0 and W0, so we're left with negative 1. So now let's clear away some space. So now what we're going to do at this point to find the new delta A, let's FOIL this term. So 1 plus alpha times delta T times another 1 plus alpha times delta T. It's going to be 1 times 1, which is 1. And 1 times alpha delta T, that's simply alpha delta T, times plus alpha delta t times 1, which is another alpha delta t. And finally, alpha delta t times alpha delta t, that's alpha squared delta t squared. So we're going to replace this term with this expression. Now keep in mind, we can add these two terms, so it's really 1 plus 2 alpha delta t plus alpha squared delta t squared. So the change in area is equal to the original length times the original width, and then 1 plus 2 alpha delta t plus alpha squared delta t squared. And now let's not forget about this one that we have here, so minus 1. Now we can cancel these two, and so we have the equation that we had before. So that's L0, W0, 2 alpha delta t plus alpha squared delta t squared. So when we use the equation L0, W0 and times 2 alpha delta t, we got an answer that was like 0.4454 for the change in area. Let's see what will happen if we kept this term. So it's going to be 12 times 8, and then 2 times 29 times 10 to the minus 6. The change in temperature was 80, plus 29 times 10 to the minus 6 squared times 80 squared. 2 times 29 times 10 to the minus 6 times 80. This part is about 0.00464. 29 times 10 to the minus 6 times 80, and then if you square it, you're going to get a very small number of 0.000005382. And 12 times 8 is 96. So, including this term, this is going to be equal to 0.44596, which rounds to the first answer that we have, 0.446. So as you can see, the contribution from this term is relatively insignificant. So thus we have the equation. The change in area is approximately equal to 2L0W0 alpha delta t. Now what about volume expansion? So let's say if we have a rectangular solid. The volume of this solid is equal to the length times the width times the height. Now, if you raise the temperature, the entire volume will increase. The length will increase, the width will increase, and the height will increase. It turns out that the equation that you can use is this equation. Delta V, the change in volume, is equal to the coefficient of volume expansion times the original volume times the change in temperature. Now, for most solids, B is approximately 3 times alpha. If you go to the textbook, you could see that it's roughly the case. It may not be precise, but it's approximately 3 times alpha. For example, aluminum has an alpha value of 25 times 10 to the minus 6, but its beta value is about 75 times 10 to the minus 6. Anytime you raise the temperature, the volume will increase. if you decrease the temperature, the volume will decrease. So let's work on the problem. By the way, this applies for not only solids, but liquids as well. A rectangular solid of brass has a coefficient of volume expansion of 56 times 10 to the minus 6. And I forgot to put the units, that's Celsius to the minus 1. So this is our beta value. Now we have the dimensions of the rectangle, so we can calculate the initial volume. It's going to be the length times the width times the height. So that's going to be 5 times 6 times 8. 5 times 6 is 30, and 3 times 8 is 24, so 30 times 8 is 240. And it's going to be cubic feet. Feet times feet times feet 3 times is cubic feet. So that's the initial volume. So now let's calculate the change in volume using this equation. So it's going to be beta, the coefficient of volume expansion, times the original volume times the change in temperature. So B is 56 times 10 to the minus 6. The initial volume is 240 cubic feet. And the change in temperature, final minus initial, 90 minus 10, which is a change of 80. So the change in volume is 1.075 cubic feet. So the new volume is the original volume plus the change in volume. So that's 240 plus 1.075. So the new volume is 241.075 cubic feet. Here's another one. A cup contains 85 milliliters of water at 80 degrees Celsius. What is the new volume at 15? So we can see that the temperature is decreasing, so the volume of water should decrease. Now we have the coefficient of volume expansion is 210 times 10 to the minus 6. So let's use the equation. The change in volume is equal to the original volume times the coefficient times the change in temperature. So the coefficient is 210 times 10 to the minus 6. It's pretty large relative to the solids. Now the original volume is 85 milliliters. And the change in temperature, the final temperature is 15, the initial temperature is 80, so the change is negative 65, which means that the change in volume will be negative. So the change in volume is about negative 1.16 milliliters. So the new volume, which is the original volume plus the change, that's going to be 85 plus negative 1.16, or 85 minus 1.16. So the new volume is 83.84 milliliters. So as you can see, it decreased slightly. Now earlier we talked about area and how to calculate it using alpha. This time we're going to talk about how to calculate the change in volume using alpha as well. The new volume is the length times the width times the height. The original volume is the original length times the original width times the original height. So therefore we could say that the change in volume, which is V minus VO, that's LWH minus LOWOHO. Now we know that the new volume L, from earlier in this video we said it's L0, 1 plus alpha times delta T. Now W is going to be something similar. It's WO times 1 plus alpha delta T. And H, if we follow the same pattern, it's going to be HO 1 plus alpha delta T minus LO WO HO. So we're going to take out the GCF. We're going to factor out LO WO HO. If we do that, it's going to be these three, which we can write it as 1 plus alpha delta T to the third power. And if we take out these three variables, we're going to be left over with a 1. So this is the change in volume. Notice that we can replace LOWOHO with VO. So the change in volume is VO times 1 plus alpha delta T raised to the third power minus 1. Now let's FOIL this 3 times. So it's 1 plus alpha delta T times another 1 plus alpha delta T times another one. Now we've already FOILed these two early in the video. We said it was 1 plus 2 alpha delta T plus alpha squared delta T squared. So now let's distribute it to 1 plus alpha delta T on the right. So 1 times these 3 terms, it's going to be the same thing on the left. So it's going to be 1 plus 2 alpha delta T plus alpha squared delta T squared. And then alpha delta T times these 3 terms is going to be 1 times alpha delta T is just alpha delta T. And then these two multiplied is going to be 2 alpha squared delta T squared. And then finally, these two multiplied will be alpha cube times delta T cube. And now let's add the negative 1. So we can cancel the 1 and the negative 1. We can combine these two terms. So that's going to be 3 alpha delta T. And we can combine these two, which is going to be 3 alpha squared delta T squared. And finally, we have this one remaining, which is alpha cube delta T cube. So we can replace this expression with 3 alpha delta T plus 3 alpha squared delta T squared plus alpha cube delta T cube. Now when alpha is small, particularly for solids, we were able to cancel alpha squared because alpha squared will be even smaller. So this term is insignificant. So if alpha squared is very small, alpha cube is even smaller. So we can get rid of this. So we can say that delta V is VO times 3 alpha times delta T. And we said that beta is approximately 3 times alpha. So then we come up with this equation. Delta V is equal to VO times beta times delta T, which is the equation that we were using for volume expansion. So you can see how it's related to linear expansion. So that is it for this video. Thanks for watching and have a great day.